Hello, my name is Jacob Misch, and I'm a postdoctoral researcher at the Rehabilitation Engineering and Applied Research Lab, or REAR Lab, here at Georgia Tech. My research today is focused on the effects of tire selection on the performance of a high-strength, lightweight manual wheelchair. I'll start up here in the rationale for study section in the top left corner. So, to briefly summarize a really complex insurance coverage system, there are 5 major categories of manual wheelchair, ranging from the standard depot chairs that you typically see at airports or hospitals, all the way to the highly customizable, ultra lightweight wheelchairs for full-time and long-term use. A high-strength, lightweight wheelchair, or the topic of this presentation, is one step down from an ultra lightweight wheelchair. Users typically get prescribed one of these if they are capable of self-propulsion in a wheelchair and require unique seat or frame sizes that can't quite be accommodated in a typical generic depot chair or lightweight chair. So the difference between the high strength, lightweight wheelchairs, again, the topic of this presentation, and the ultra lightweight wheelchair is customizability. Whereas the ultra lightweight chairs are custom fit to the exact size and shape of the user, and they're given a large selection of frame types, of wheels, of tires. These high-strength lightweight wheelchairs are typically only available with one set of components, and possibly only 2 or 3 seat sizes without much other customizability. They might have 1 or 2 positions to put the drive wheel axles, but that's about it. And thus, users are either stuck with typically cheap components equipped by the manufacturer, or they have to pay out of pocket for what we'd like to consider better components. The objective of this work was to see how much better one of these chairs could perform with just swapping out these components, these casters and these drive wheel tires. Next, I'd like to move down to the experimental design section in the bottom left corner. So our experimental design was fairly simple. We used one high-strength, lightweight wheelchair frame, and this is a Viper Plus GT from Drive Medical. And we used the default components provided by the manufacturer. These were actually in this picture here, the 8 by 1 inch unbranded casters in the front and these solid pyramidal tires as the rear drive wheel tires. These are also in this table here, 24 by 1 inch solid mag tires for the drive wheels and the 8 by 1 inch unbranded casters in the front. We then took a look at some studies on similar components, ones that were similarly low maintenance, and what I mean by that is non-pneumatic or solid tires. And we selected a pair of casters and drive wheels that had low rolling resistance and scrub resistance over some common interior surfaces. These components were the Primo branded 6 by 1.5 inch casters and the Primo Express 24 by 1 3/8 inch Primo Express drive tires. So with these 2 sets of casters and 2 sets of drive wheels, we generated a small factorial design with 4 different configurations. Configuration A used both sets of default components, the 8 by 1 and 24 by 1 solid components. Configuration B swapped out the default casters with the 6 by 1.5 Primo casters. Config C swapped out the solid mags for the Primo Expresses, and configuration D used both Primo branded upcharged components. Next, I'd like to move to the amps, the main section in the middle. So data collection was conducted with the Robotic Anatomical Model Propulsion System, or AMPS for short. This is a machine that emulates the size and shape of a typical male wheelchair occupant. It has a motor on the end of each of the arms. You can see here, and the inset image also shows the motors. These motors interface with a custom ring gear that we use as a push rim on the drive wheels. A control system within the amps allows us to configure the exact output of the motors. So we have a high degree of control of the speed and direction that we drive the wheelchair. This, of course, gives us a near infinite array of possible maneuvers or trajectories that we can drive the wheelchair with. In this study, we opted to drive the chair in a straight line over a 10-meter distance, roughly. The amp supplied the wheel torques, seen in this figure up here with the blue line. We collected 10 trials of this maneuver, the straight maneuver on linoleum tile, and 10 on a high-traffic, low-pile carpet for each of the 4 configurations. It is important to note that every configuration, config A through D, received the exact same torque profiles for tile and for carpet. So if one went faster or farther than the other, it's because it was easier for that chair or that configuration to accelerate using the same torque profile. Again, the wheel torques are right here in this blue line of the image. Next, I'd like to move down to this section here, the propulsion cost, up here to the top right, propulsion cost calculation. Our main outcome metric was propulsion cost, or the amount of work that the amp supplied to the chair during each trial, each maneuver, divided by how far the chair actually traveled over ground. You can think of this as sort of an inverted miles per gallon for an automobile. This is sort of like gallons per mile in a way. So joules of energy per meter that the chair travels. Of course, a lower propulsion cost means less energy is required to travel per meter. And this is, of course, a better performance. So we're looking to lower this propulsion cost, lower the amount of work, or raise the total distance that the chair travels. Next, I'd like to move down to propulsion cost differences in the bottom center of the slide. Differences between the configurations were relatively large and pretty apparent. Some basic trends can be seen here in this figure. Carpet, the blue data, is generally higher than traveling over linoleum tile. And this is because carpet, if you've ever propelled a wheelchair over carpet, it's just miserable to try and push over. You sink in, and it raises the amount of effort you need to put in to travel across the surface. So carpet's harder to propel over, has a higher propulsion cost. The default components, configuration A, have the highest costs on both surfaces. Changing either the caster or the drive wheel to the Primo branded variant improved performance. You can see this in both carpet and tile. Upgrading the drive wheels had a more consistent benefit to performance. You can see this in the carpet data, whereas the casters suffered a little bit of performance going over carpet. And changing both sets of components to Primo branded variants had the lowest cost on both surfaces. So there is reason to believe that upgrading the default components can lower propulsion costs and increase performance. Ultimately, this changing all the components going from config A to config D reduced the propulsion cost by over 40% over tile and over 17% on carpet as compared to the Drive Medical default configuration. Next, I'd like to move over to the discussion section. These results allow us to assess what we'd like to call value of components. And this is possibly the first time the idea of value has ever been linked to components and manual wheelchair performance. So the large default 8-inch casters cost $23 per pair. The default solid mag, solid pyramidal drive tires cost $34 per pair. The upcharge Primo variants are $42 and $48 for the casters and drive wheels, respectively. What this translates to is a $19 price differential to buy Primo casters instead of the drive default casters. And this amounts to a 24% performance boost due to the better casters over tile. Using this logic, there's only a $14 difference to boost by a similar amount with the Primo drive tires. And there's a whopping $33 difference to get both of these Primo components instead of the drive counterparts and boost performance by up to 40%. This is massive and should really lead the way to insisting that manufacturers upgrade their performance for the benefit of the end users. Obviously, there are so many items involved with this research that I can't cover in this video. If you have any questions, please join my session from 4 to 5 p.m. on Tuesday, September 28th, or email me at mischjp, that's MISCHJP, at gatech, GATECH.edu. I would be happy to answer your questions and discuss this work at your convenience. Thank you.